Hi, I'm Jamie Hicks, and today I'm going to talk to you about easily emulating full systems on Amazon FPGAs, full SoCs. How many of you are specifying, designing, or developing software for new SoCs? How many of you were doing so at the start of the pandemic? And wouldn't it be nice to be able to do so in the cloud? Did you know that Amazon Web Services rents servers with FPGAs in them? In this talk, I will tell you how we validated our RISC-V CPU and made it available to others by running Linux on it in an Amazon F1 FPGA. So the context for this work is a DARPA program named SITH, which is about security enhanced hardware. And I was on the MIT CCL team where we were taking an approach of which we called sanctum enclaves. The goal for a sanctum enclave is that software running the enclave is isolated from other software as if it was running on a separate machine. So that, and in the full part of the program, we verified this with theorem proving and model checking to show that it really was. We could show what the properties were that was needed to show to guarantee that, and then we could actually show that parts of the design actually met those criteria. In kind of a broader context, Arvind's team at MIT developed many RISC-V variants in BlueSpec from a microcontroller that was fabricated, actually a couple different versions in carbon nanotubes, several in-order cores that they used in teaching for undergraduate and graduate classes, a speculative auto-order processor called RISC-V, and then an enhancement to that with sanctum hardware isolation, which was called MI6, which prevented side channels due to speculation and shared resources such as caches. For the SITH program, we started with BlueSpec Inc.'s Flute RISC-V processor. It's an RV64GC. We wanted to start with a common baseline. Several teams were using BlueSpec. We all started with Flute as the baseline processor and then enhanced it with different security enhancements. We added enclave support and a variation of tagging. But in this talk, I'll focus on the enclave support to Flute. And other teams such as SRI Cambridge, they added their Cherry capability-based hardware extensions to Flute. And so that's kind of the context for the work. We were working with Xilinx VCU 118s, basically in a lab on a bench, attached via JTAG and UART and Ethernet to the outside world. Another team in the program provided a Vivado block design that contained the I/O devices, the UART, the Ethernet. We had file system and RAM disk, no actual block devices. There was PCI Express extensions available. We basically plugged our CPU cores into a fixed socket inside of that design, generating Verilog from Chisel or BlueSpec or handwritten Verilog. MIT team, SRI Cambridge, we used BlueSpec. And one of the downsides of this was loading GDB and especially loading a RAM disk over JTAG was quite slow, but it worked. So that was what we used for the first year and a half or so of the program. But last February or so, we learned that we were going to run a bounty hunt where outside people could try and exploit the security vulnerabilities, anything they could find. And so we had to be able to make these on demand to many experts who were going to be trying to find holes in the designs. And so that meant something more scalable than the VCU 118 sitting in a lab. So we were going to run them on the Amazon F1 FPGAs. And we still needed the same software model. So we needed a UART Ethernet block device. We wanted to be able to debug things. And one of the constraints, a couple of constraints from Amazon side, there's no Ethernet connected to the FPGAs. There's no block devices connected to FPGAs. There's really PCI Express from the FPGA to the host. There's DRAM in the FPGA, and that's what you've got. Since there was kind of a gap in terms of who was going to work on this, I took the opportunity to say, well, let's try and make it more flexible than what we had. And for one thing, speed up the loading of code and having a real block device. But we also had the goal of getting this working as fast as possible. It was kind of a side thing compared to what we had committed to doing. We were still focused on hardware, security enhancements, and the software to make that work. And so we wanted to try and minimize the distraction in terms of implementing this. So here's a block diagram of how we approached it. On the host side, since we weren't doing any security enhancements to the device drivers, we decided that let's just do them in software and then connect them up to the hardware. And also we had to have some amount of host software anyway so that we can connect to files in terms of a block device and to the network. We did actually want to connect to the actual internet through Ethernet devices. So here's the core of the left-hand side. All that stuff in blue is written in BlueSpec in Bsv. Here's the MIT Enclave enhanced version of the core. And it has the debug module interface. There's a tandem verification interface that we could use to debug the core. And one of the DRAM banks, DDR bank A, which connect up to 16 gigabytes of DRAM. The middle yellow block there is the FPGA shell, which is what Amazon gives you as the interface. It's a fixed part of the interface, which I'll get into in the next couple of slides. But also, the SRI Cambridge team made their design work in the same setup. We made a slight change to the interface because they wanted to have all writes to DRAM go through their L1 cache where some security checks were done. And because the whole thing was done in BlueSpec, that part was pretty easy to do as a variation of the implementation of the interface. So just kind of some of the high level points. We have the Amazon shell. It provides the PCI interface to host using Virtio device models. And I'll got a few slides on that later. But basic goal was reuse open source implementation, reuse drivers, enable DMA transfer, and all with minimal work. And then another point was through the shell, we could use DMA to load the program instead of using JTAG. So it was much faster to get things started. The CPUs that we implemented only run at 100 megahertz. They're not really, there's no work really on optimizing for speed. This is all about making sure that the hardware security enhancements were actually secure. For these designs, these teams of the program, everything was implemented in Bsv. How easy was it? I'd argue it was pretty easy. I think I started at the beginning of March and wrote 400 lines of code, hardware and software, so that I could have the MIT processor running on an Amazon FPGA with the debug module interface, so I could load code and control it. This is not full featured, but it showed that this approach actually worked. Then in April, we added the vanilla BlueSpec and the SRI Cambridge variations. Implement a faster offloader that used DMA direct access to the FPGA DRAM. Plumbed in the I/O models with TinyMU. There was some exploration of threading and so forth to make that perform well, but the hardware interface was pretty straightforward. Jessica Clark from the Cambridge University team helped on this. Essentially, this whole thing was part-time effort of the two of us. In April, I also debugged the MIT Security Monitor, which I hadn't run before that. It had been under development for months by one of the grad students. Under development on QEMU. So it was developed and debugged in QEMU, and then a little bit of work to system integration to get it onto this hardware, some work getting different file systems on there, and testing it out. By the end of May, we started deploying to testers outside our own teams, and with Galois and to the team running the company running the bounty hunt. In June, we got GDB stub. BlueSpec released their GDB stub, and Jessica integrated it, and so we had a kind of full-featured development environment now. So part-time, a couple of months of work, and did what we needed to do. I was pretty happy. So let me talk about the key pieces. So I've got a slide on the Amazon FPGA shell just to show the details of that, high-level details of that. some slides on Connectal, which was, I think, for me, it's the way I do things, so it's a key ingredient. But MIT team, MIT students and Cornell students have both used it. On the Cornell students, he said he wouldn't graduate if he hadn't had Connectal. I'll talk about Virtio because it is kind of obscure. And Bsv and Vivado were also key ingredients. Vivado is the tool for building your designs for Xilinx FPGAs, and BlueSpec System Verilog is the language that our team uses, and that I use predominantly. So the Amazon F1 shell. Here's a picture from their documentation of the shell. So it provides the host interface through PCI Express, which is how the FPGA connects into the server. And if you've done any work with PCI Express, you know it's kind of grungy, detailed work to do anything useful with it. So it's nice that they've packaged that up with an AXI bridge and split it out into multiple interfaces. We use there's a couple of 512-bit interfaces, one that's host CPU to the FPGA, DMA PCIS. We use that one. There's one oriented towards DMA from the FPGA to the host memory, the PCIM, which is also 512-bit. In this design, we didn't have a need for that. And then there's some 32-bit interfaces, which are really oriented towards control and monitoring. And we use the OCL port. Excuse me. There's 4 banks of DRAM with 16 gigabytes each. We used one of the banks. We weren't running giant programs, so there wasn't a need to connect more. And we used DDR Bank A. This picture shows inter-FPGA serial connections. If you're using the multi-FPGA servers, we weren't using multi-FPGA servers, and I think they've actually never exposed this to customers. In addition to breaking out the interface into something that's kind of more easily usable by designers, they also have some kind of firewall functionality in the shell, so that you can't to make it harder for you to crash to the server, and especially not to crash the actual physical server, not just your own VM, because they do have servers with multiple FPGAs in them, and those are shared between different customers, and so they need to defend against inadvertent or advertent attacks on the host system. So let's see, I talked about memory map. Right, we memory mapped DMA PCIS so we could access it, and we didn't do DMA. Right, they call this the CL box is customer logic. This is our design, is the customer logic. So back to this picture. Generally, we expose the DMA PCIS through our standard device driver. And mapped it into the host software so it could read and write DRAM directly, or through the L1 cache, depending on which design was in there, and use the OCL 32-bit port for Connectal messaging. So let me talk about Connectal. Because a big part of what made it easy to get this running was that Connectal already ran on Amazon FPGAs. And Connectal is a project I started in 2012 or 13. I was doing some exploration with a Xilinx Zinc FPGA, and I read the instructions for, I want to write a piece of software and a piece of hardware and have them work together. And there was like 52 steps to make that work. And I just thought that was crazy. So one thing was, in the middle of that was write a device driver. And I'm like, can't I connect them without writing a device driver? Why? What's so special about needing a device driver? And also from doing work with Bsv at Nokia Research, wouldn't it be nice if and also from working on many device drivers, wouldn't it be nice if there was something, if we could use kind of more modern technology here. If we're doing distributed systems and software, we would have an interface spec and we'd generate stubs, and those could be in different languages. The compiler would verify that your use of it is correct, is consistent with the interface, and vice versa on the other side. Couldn't we use that kind of approach in the hardware software approach? So that's kind of the key idea of Connectal, is we specify the interface between hardware and software with an interface spec, what we'd call an interface description language. But it turns out there are many interface description languages. There's none that's really generic and globally usable. So we ended up using Bsv interface specs, interface declarations, as the interface spec. And I'll talk about how that works in a couple of slides. And also, we want to be able to if we're doing something simple, we want it to be simple. We want to be able to write some user space software and have it talk to a piece of hardware that we load in the FPGA. We don't want to have to write an app-specific device driver. And that's kind of the core idea. As coming at it from the software point of view, we want to be able to think of it as asynchronous remote method call interface, because that's something we could do generically through the device, through the hardware interface, through a common device driver. And it fit the model of having, you can't do a synchronous call to hardware for any operation that's going to take some time. You've got two time domains. So asynchronous remote method call fit our notion of how to approach that boundary. Software makes a call to hardware or request to hardware. Hardware does something. A while later, hardware calls back to software and says, here's the answer, or I'm done. Here's where to look for the answer. In terms of making it easy to do something simple, it got down to, instead of 52 steps, there were like two things to install. You had to install two big things to install Vivado, install BlueSpec, which was closed source at the time. So those took some time, but then, installing Connectal was, apt to install Connectal. Then after that, you'd write 3 files. You'd write a C++ file, you'd write a Bsv file with your hardware, you'd write a make file that says, here's what the interface is for connecting the two, and you'd say make build.zboard. And it would build the design, the hardware and the software pieces, and load them on, make it so that you could then run your software. It would load the FPGA, and away you go. So it seemed like you couldn't get much simpler than that for something that was hardware and software. I guess it could be one file if you had a common language, but I guess I wasn't willing to make that leap. I didn't want to force hardware and software to be the same language. So we've done C++, we've done C, we've done user space, we've done kernel space. We've even exposed this interface through WebSockets so that the software could be in a browser and the hardware on hardware and FPGA. So I wanted to retain that flexibility. It didn't have to be a single language, but once you got down to that point, it was pretty minimal. And it also made it portable across Linux and Altera, different operating systems, Linux and Android, user space and kernel space. We don't want you to have to write a device driver, but if you're doing an accelerator on a file system or on some sort of file system accelerator or database accelerator, it might need to be in kernel space. And so then you want to be able to do that. And you will have to write kernel code. But then it's a requirement of the application, not of being able to use hardware. So that is the philosophy and the background. And now let's talk about a bit more of the detail. As I said, I started with the debug module interface on this thing. So let's start with that interface. So on the request side, we're going to be able to read, write, and check status of the debug module. And then response side, after we send a read request, we get a DMA read data response. And we send a status request, we get a DMA status data response. And I think there's a write response that's just for ordering. It doesn't actually return any data. So this is actually Bsv code. It's an interface spec. It looks kind of like a Java interface spec, but the types are different. And method action. Action means that this thing on the hardware side operates synchronously. DMI read takes 1 clock cycle when it fires, and it doesn't return any values. And so that was part of our we knew that if we let you provide a value and a response, somebody was going to try and abuse that. So remote method invocation, you invoke a method, it does something, later you get a response back, which is another method invocation. This makes sense for somebody who does software, especially distributed software, but I'll talk about how we view that from the hardware point of view, I guess, on this slide. So in this picture, the red boxes are generated from those interface specs. So from the request interface spec, we have a request proxy on the software side. This is something that software makes calls to. So the DMI read in main calls against the request proxy. That takes the arguments and packs them up into a struct. And it packs them on the software side as to the how the bit fields lay out in the hardware side. Then it enqueues them into a FIFO. In case of Amazon FPGA, it's PCI Express memory interface into memory mapped FIFOs in the hardware. Then there's this request wrapper that's generated by Connectal from that interface spec. And that calls into the method interfaces on the user hardware. The user hardware, in this case, being our whole CPU and its debug module interface and all of that stuff. So Bsv code for snippets of kind of the system interface of our design on the hardware side, there's a method which is the DMI read method, and queues into the CPU. DMI engine says, do a read request of A. Then a rule, which is kind of an always block in Bsv. When there's a response, it pops it out, and it calls this indication proxy with their DMI read data. So the indication proxy is another piece of Bsv generated by Connectal. Package up, it's the same like the other proxy. Package up the values into a message and queue them into the FIFO. Split them up into 32-bit words because we typically use 32-bit FIFOs. And if when the FIFO has something in it, it will raise an interrupt so that it can wake up the CPU. On the software side, there's indication wrapper, which does the dual of that, unpack it, and then call back into the user software, called the DMI read data method. User generated is in blue, and Connectal kind of build scripts generated is in red. We have the hardware software portal. I always have to think, I get confused. So that's sending messages from hardware to software. And so I think of it as method invocation. You can think of it as message passing, or we're just enqueuing data into a FIFO and dequeuing data from the FIFO. But think of it as enqueuing messages, even though it's a 32-bit FIFO, 32-bit wide FIFO. The messages may take multiple entries in order to fit all of the values. And then the software hardware side. So they're very similar. In some ways, they're duals, but in terms of the implementation, they're not exactly the same. But in terms of the logical flow, they're exactly the same. We make method calls across, we send messages across, however you want to think about it. But that's worked out really well because you can adjust the interface spec, and then when you compile the two pieces of code, the software and hardware, if they don't match the spec because you didn't update them when you updated the interface spec, then you'll get compilation errors, and so you'll know that they don't match, and you'll fix them up. In our usual kind of deployment, our usual being to FPGA boards that are plugged into processors, we would actually plug the bit stream. We would actually append the bit stream to the host executable, so that you made sure that they were built together and that they're consistent. That's not really an option, as I'll talk about with Amazon, but we, as much as possible, we try and follow that model. A few more details. Of course, user space doesn't get interrupts. So in the Linux kernel device driver, the interrupt service routine hooks things up so you can call the poll system call. Host software calls poll, and which actually goes to sleep and waits for interrupts. And and that then delivers, that then wakes up the user software, which is really, it's an event loop running in a separate thread, usually, and wakes up that thread, and the thread goes in and says, what messages do I have, and unpack and invoke the appropriate methods in the user software. That interrupt step waiting for interrupt is optional. If you know you're going to get lots of messages and the interrupt overhead would be too high, you can just pull directly on the FIFOs to see if they have data. But often, and in this case, it's not that often, so you'd rather the CPU go to sleep, wait for interrupt, and then process events as they come in. So that's kind of more of the details. I guess important detail here is we do typically have multiple threads with an event loop thread that's handling responses from the hardware. Those FIFOs in hardware are not infinite in size, so it's actually really useful to make sure you make forward progress by having a separate thread for handling events from hardware and threads for delivering requests to hardware. And as I say that, I'm immediately going to turn around and say, well, sometimes the requests go the other way. But we'll come back to that. So this is the C++ that's generated from that part of the interface spec. And so it's just a class, and for the proxy, you can invoke the methods of the class. The callbacks, again, the response proxies, instead of calling a class that it's provided, the request proxy, you define a subclass of the response interface, and then the wrapper code will invoke your handlers for the different callback methods. BlueSpec side, here's what you'd write. You'd expose these methods in BlueSpec. The ports that you expose for a module are generally exposed as methods, which maybe the closest analogy I have for the hardware side is it's an AXI stream interface, and where you've packed the arguments of these methods into the data that's in the AXI stream. And where it says method action, that means this method runs atomically on a clock cycle. And so in terms of AXI stream, that's when your ready, valid are both asserted, the method fires and things happen. So that's kind of the hardware-centric view of it. But often we think of it as, it's an atomic piece of code that runs when it's ready to fire, when it's got data, and when it's able to fire. Next, I'd like to talk about the Virtio device models that enable us to model the I/O devices in the host software and connect them up to our RISC-V CPU in the FPGA. We decided to use Virtio as the approach because we could use TinyMU, which is a small virtual machine written by the same author as QEMU, which is a widely used and very high performance virtual machine. TinyMU implements Virtio device models, among other things, but that was what we were going to focus on. It's open source. Because it's a simple virtual machine, it's looked like it would be reusable. We'd be able to use the device models without having to do much surgery to pull them out. And that turned out to be true. An advantage of Virtio is that it's a standard model. There's Linux drivers, there's FreeBSD drivers. The Cambridge team was using FreeBSD. And so we didn't have to do any work on the Linux side, at least on the device drivers. And FreeBSD, there were some patches needed because it implemented an older Virtio spec. The other nice thing about Virtio is it has a spec. It's not just something somebody wrote and threw out there. So, as I said, we want to use an approach that enable us to reduce device models to be a software problem and then make it be a non-problem by reusing existing device models and drivers. And TinyMU and its drivers seem to fill the bill. So what is Virtio? It's actually a common framework that was developed for I/O between guests and hosts and managed by hypervisors when you want to actually improve performance based relative to emulating some existing piece of physical hardware. So it's a pretty generic model. It provides a variety of devices. The ones we were interested in were block, network, randomness, entropy, and console. It has drivers for Linux and FreeBSD and probably other operating systems. But those are the two that were used by teams in the SITH program. And it's actually used by KVM and QEMU. It was a way for them to have a common interface so that guest operating systems could have device drivers without having to change the drivers for the different underlying hypervisors. Normally in a virtualization environment, there's a set of memory mapped registers for each Virtio device. It's mapped into the guest operating system. There's a register that identifies what kind of device it is, which instance it is, what the capabilities of the model device are. And then there's pointers into DRAM for request queues where the actual operations take place. You can queue a request to like read a block out of a block device. Then the host looks at the host is trapping reads and writes to that memory mapped registers and processes the request from the queue because it can access the same shared memory. So that actually fits our model pretty well, that the RISC-V CPU can access the registers and the host software can access the memory and those registers as well. So it's like our RISC-V was a guest, and except the difference is our hypervisor is user space code. And in the host, we have a file per block device. We have dev ton, which ton tap interface, so that the host software can actually send and receive packets on the physical Ethernet. And there's some flexibility there if you want to do a bridge interface or a NAT or whatever. That's kind of outside the scope of this talk. But it's a standard interface, and so we could actually set it up so that researchers could SSH into our RISC-V CPUs. Researchers being the bounty hunters. When you're physically on the machine, you could use UART connected to a pseudo terminal. I think there was a way that the UART could be exposed out to a socket for the security researchers, but I think primarily they used SSH to access the machines. How did we connect this up? Going back to the Connectal interface, the registers were exposed. The registers, which are modeled in the host software, the TinyEmu code, were exposed to the RISC-V CPU via an Aws interface. And here the interface names are kind of backwards. The hardware to software requests are in what was called the response interface. Probably I should separate them into a separate interface that is supported. So it could be the Virtio request interface. But in any case, requests are coming from hardware to software. And it's just regular Aws looks very familiar, AWADder, ARAdder, the signal at the beginning of a request to read or write a particular address range. IOW data, which is the write data that would be going along with the write request. In the other direction, the responses come back from software to hardware, from the device models and the host software to the RISC-V CPU and the FPGA via our data of each word of data that's responded to a read request and be done to signal the end of a write request that has been completed. So this interface is for the control registers. Shown here in the upper one, AXI-MEM by Connectal. That's that AXI interface for the control registers. Effectively, it looks like an AXI slave via the FPGA shell interface that reaches down into the registers that are implemented by TinyEmu in the host software. The other direction, the access to those queues that are shared between the Virtio model, device model, and the RISC-V CPU, those queues are actually in the DRAM DDR bank A, and TinyEmu can actually access it directly through the x86 CPU load and store instructions, read and write instructions, because we mapped that DRAM into the host software via mmap. And a little bit of generic code in the device driver to enable that, but it's just mmap. So that's kind of the Virtio stuff in a nutshell. As I said, it was straightforward and got us the capabilities we needed in fairly quick order. So now I want to spend a little time talking about how we built it on AWS, and I'm going to talk about some of the mechanics of AWS accounts, just in case you've never done it before. I know among the different people working on the Sith project, it was new. I'm like, but haven't you had an AWS account since 10 years ago? It's very common for some people and very unknown for other people. So anyway, so let's talk about building on AWS. Now, before I talk about that, it's not actually required. We did a mix of building things on AWS and building on machines or our servers in our own premises. You have to have Vivado installed, and if you don't have Vivado, that's a 16 gigabyte, 20 gigabyte download. So the advantage of building on AWS is that if you haven't done it before and you don't have those things, Vivado set up, then you can actually jump in and do this very quickly. If you're doing a lot of builds on AWS, it can get expensive. But if you're doing like, I want to try out this project and I want to spend a few hours building it, and I don't have to spend any time installing tools, then building on AWS works really well. And so I actually do a mix of, sometimes I build on AWS anyway, and sometimes I build on servers. So kind of the basic things needed to build it, wherever you build it. You need a bunch of pieces of open source. And I say that this entire thing is open source, but that's not exactly true. On the closed source side, we have Vivado. There's the actual design checkpoint that implements the F1 shell. Those things are closed source. There's some IP cores that are from Xilinx that are closed source. But all of the actual design part is open source. So you need AWS FPGA, which is a Git repo from Amazon that includes like Verilog header files that say what that interface is to the FPGA shell. This has actually changed since that project started. The next thing, Bsv Compiler, now we use the open source one. It used to be a closed source thing. You used to have to get a license from BlueSpec Inc. So Vivado and BlueSpec compilers were kind of things that took a while to get through, to get done before. But now BlueSpec compiler is open source. So that's in that camp. Connectal, fully open source. Our processor, the Flute, basic version from BlueSpec, our MIT version, the SRI Cambridge Flute Cherry, those are all open source. And then this repo, Sith AWS FPGA, which is kind of this whole collection I've been talking about today, assembled into one repo, hardware and software, and build scripts, just to make it reproducible. And partly that was, in order to make this approach workable across multiple teams, we need to have a common repo and submodules of all the pieces so that we could be keeping track of consistent versions and moving forward as we added features. And then also it turns out to be useful in case anybody else wants to try it out or derive from it or reuse any pieces of it. The whole repo is there, has some documentation. Being able to build it is something that other teams have done with not too much work. If you do build on Amazon, there's a Amazon FPGA developer instance machine image, which includes Vivado and a Vivado license for Amazon FPGAs. So that's a way you can say, I want to try this out, and all I need to do is create an account and launch an instance and run the tools. You need two resources. Amazon has so many different kind of facilities. We need two things. We need EC2 instances, servers. We need an S3 bucket, which is a storage facility for blobs of data. I'll talk about why we need that in a bit. I have kind of this notion that if I want to try out a new kind of piece of software, I want to be able to, in a day, get started, try it out, and see if I want to proceed. And this project, it's more than half a day because it takes like 4 hours if you're building this design to build it. So this one, this is if you want to try it out, probably a multi-day effort. You don't have to spend multiple days, but it will elapse time, take multiple days. So if you're starting from scratch, and some of the people in different teams were, first you create an account. You go to aws.amazon.com, click on the create button, work your way through the next few steps. In a new account, you get access to you get some credits, and there are free tier level of instances and so forth. Unfortunately, the build, if you're going to build on Amazon and if you want to run the FPGA on Amazon, they're not free. But it's like 75 cents an hour for a build machine and $1.50 an hour for an FPGA. So it's pretty cheap if you just want to try it out and kick the tires and see how it works. So that's the first step. Then there's kind of things you might not think about. So I've highlighted them here. You'll need a key pair, an SSH key pair. And so that's, after you create the new account, you end up here, you click on EC2 and you end up here. And so we want to select the key pairs button, which takes us to this next thing, create a key pair, give it a name because that's going to be the name of the file and it's going to be in your .ssh directory. So you want to know what it's for. So I made an account for AWS RISC-V Summit. I made a key pair to go with it, download it in PEM format, assuming you're using OpenSSH, Mac, Linux, whatever. If you're using PuTTY on Windows, then I guess use PPK. So anyway, download the key pair. Don't lose it. You'll be downloading the private key, and Amazon will keep the public key. And whenever you launch an instance, Amazon will install the public key as an authorized key, so you can SSH to it. So that's one key thing. Copy it to your SSH directory, do your usual SSH management of that key. So when you log into things, the next thing is to, at the last step of the build, and this is the same even if you're not using Amazon build machine, but anytime you build an Amazon FPGA image, the last step is you copy it up to S3, and then Amazon infrastructure does the processing of it and publishes an Amazon FPGA image. So you have to create AWS keys so that you can access AWS resources through the API, I guess. We're going to use the command line interface in a script to do so, but it's through the API. So again, I guess if you haven't used Amazon, everything you can do through the console and more, you can do through APIs. And then you can use command line versions, you can write Python scripts, and basically you can script the deployment of thousands of servers if you like. So anyway, so here, when you create the AWS key, this is even more important than the SSH key. You want to keep control of it, because if you give it privileges to launch servers, then you lose the key and somebody else gets it. They can launch servers on your credit card. So this page shows if I just went in straight and I, with my root account, create an AWS key, an access key, it would be this page. I didn't really want to get into it, but you should, they recommend create a user that's not the root, and then create an access credential for that. And I do recommend that. So then you can say, this user has access to EC2 and S3, but nothing else. And it's also easier to kind of revoke that key as opposed to a root key. So despite my pointing to create the access key for root here, I recommend going in, create a user, give the user access to all EC2 and all S3, because you want to be able to launch instances, and you want to be able to access S3. And create the AWS key, download it to your .aws credentials file, and we'll talk about what you need to do with that. And right, here's the second step. You create the access key and it downloads it to you, and you can show it so that you can copy it into a file. The script can work from environment variables or files. The .aws credentials file for me has been more convenient. And then just kind of the first step of, if I was going to launch a developer machine, I would go into that services button, click on EC2 for the kind of service, and then select instances. On that page, I can say launch. That's all pretty straightforward. The next thing is I want to choose an FPGA developer, AMI. So search for FPGA developer. It's one of the marketplace ones. Select that. And then the next page, it will give you options to choose what kind of instance. There are many kinds of instances now. They recommend Z1D to extra large. I don't remember what Z1D means, but to extra large means it's got 8 cores, I think 64 gigabytes of memory, something like that. So it's pretty beefy, but you actually need it because this is a big FPGA and Vivado takes a lot of resources to build for it. Vivado will complain if you choose one smaller than this with less memory than this. So I recommend this. I think it's 75 cents a minute, an hour. 75 cents an hour. It's not too bad. A build is going to take 4 hours. So even if you build on AWS for this thing, it's not too much money to try it out. It is unfortunately beyond the free tier. So as we say, we go through, and I think those two choices, which kind, and then which Amazon machine image and which kind of image, which kind of instance, are the only things that really matter in this selection to enable you to launch kind of a generic build machine. In the last step, it will make you acknowledge that you have the Ssh Key Pair that it's going to use. So then you need to copy your AWS credentials to that machine, because the build script uses the Amazon AWS command line interface at the very last step to do a bunch of operations. It uploads the design checkpoint that results from the build to an S3 bucket, and then it tells Amazon through another call to create an FPGA image from that S3 bucket. So those two operations need the credentials. I did a build recently where I forgot to copy the credentials, and it got through the end. It was like, oh, I failed, and that part needs some more restartability. But anyway, so make sure you copy the things there. I'm going to fix the script so that it checks for them before you start, and doesn't let you run a 4-hour build and then tell you that it couldn't actually upload. So these are actually all the steps. If you copy your credentials, you do git clone -- recursive because it's a bunch of submodules. I made a branch for the summit here so that I could make some. So actually, I added this build script for this summit. So check out this branch of Sith AWS FPGA. It will check out a whole bunch of pieces that includes both hardware and software. This step of the build, we're just going to build the hardware pieces. So since it takes a while, I run it under screen. So I start screen, then change into the hardware directory of this repo that you just checked out. Then sudo install deps. And this is going to install a few things that are needed in order to build the software. That FPGA image includes almost everything you need. I think we include a utility. We installed I forget what we installed. We installed just a small number of extra things. Some Python libraries that are used by Connectal. So that gets installed there. You can look at the script. You see it's pretty benign. And then run build.sh. Now in a standard Connectal build, I would actually type out the whole command, but the FPGA developer image is based on CentOS, and it's not even very recent. So the libraries in CentOS are too old. In particular, the Haskell compiler is too old to build the open source BlueSpec compiler. So this is kind of a new problem for BlueSpec, but it's actually solvable. So, right, I remember we installed Docker. And so there's a Docker image that contains the BlueSpec compiler. And this build script splits up the hardware build into 3 steps. Does the standard Connectal step to generate the stubs and all the generated files from the interface and the makefile. Then it runs the Verilog, the compilation step that goes from BlueSpec to Verilog inside a Docker container, so it can have access to modern Haskell compiler libraries that are needed by BlueSpec compiler. And then at the last step, it runs Vivado natively, because Vivado is resource intensive. Runs Vivado natively to synthesize, place, and route the design. And then the last step calls, let me talk through this slide, which talks about all these steps. Right, so first we generate the Bsv and CPP stubs to make sure we have all the code that we want to compile. We're actually not going to compile the software on the side because we're going to recompile it for the target machine when we run the design. Compile the Bsv, generate Verilog. This script does it in a Docker container so that it will work on CentOS as well as Ubuntu. On Ubuntu, you don't have to do the Docker container, but that script is now generic. The third step is it runs Vivado to synthesize, place, and route the Verilog inside the Amazon FPGA shell. And it takes several hours on this design. It takes a while, even on a minimum, even with hardly any logic, because there's some amount of processing Vivado has to do with the shell. And it's a big FPGA, so it has all sorts of options of where to put things. But it takes a while. That's why I run on screen, so that if I get disconnected from SSH in the middle of it, that I can reconnect to the, I can SSH, do a screen -R to reconnect to the session, and I haven't interrupted the build. During your 4 hours, you can go off and do whatever, have a cup of tea. So at the last step, it writes out a design checkpoint, and then uploads that to S3. And you can, generically, you can tell it whichever bucket you want. Connectal uses a bucket named AWS FPGA. A bucket is just a container that you put objects in, and they can have names. And so, I don't know, it's just terminology. It's just that you have to agree on the name. So it uploads to the bucket, and then it does another AWS call and says, create an FPGA image from this particular file object that's in the AWS FPGA bucket. So it needs your AWS credentials for that step. Now, as I said earlier, even if you run this on your own on-premises device, wherever, your own server someplace, this step talks to AWS, because that is the step that creates a bit stream. There's not like a bit stream that you see in a file and you can move around. In the infrastructure, Amazon creates bit streams, and then they tell you an FPGA image ID, an AFI or an AGFI. AGFI is a global name for your bit stream that's portable across data centers, across availability regions. And AFI is a name for it in your local availability region. That last step takes 30 to 60 minutes. I know part of it is doing a partial reconfiguration, do a diff against a bare Amazon shell in your design to get the partial bit stream, but it also runs a lot of design rule checks to make sure you're not going to crash the FPGA, you're not going to overheat the FPGA. I'm not sure what all they check for, but we know that they check for things. They check for combination loops, because that can create little hotspots. Typically, it seems to take 30 to 60 minutes, depending on, I guess, load someplace. It's kind of opaque. But that step has to happen in AWS if you're going to use an AWS FPGA. It doesn't matter where you build it, but you have to use that step. So now that you've got a bit stream someplace and you want to run it, what do we need? Well, we're going to check out the whole same source repo, because it's not that big anyway. But this time we're going to build the host software. And if you're actually going to run this thing, so here the next two pieces are, you need a RISC-V Linux kernel and a RISC-V root file system that we're going to use for the device under test for that RISC-V and the FPGA. And you need an FPGA, an Amazon FPGA. So you need this is an Amazon only thing. An Amazon AWS F1 FPGA instance. There are, I think, 3 sizes. The smallest one is F1 2 extra large. It contains 1 FPGA. If you want to do multi-FPGA things, you can get a, 16 extra large, and it has 8 FPGAs, I think. I think they only can communicate through PCI Express. So you're sharing the host across the multiple FPGAs. I think in the hardware, they have some Aurora fast serial links, but I don't think anybody's been able, I don't think those are exposed to customers. I'm going to recommend choosing Ubuntu 20.04 or Ubuntu 18.04 for this step, because that's what we developed on, and so it's easy to build the host software there. We need, it's not like we need anything super fancy, but we need like CMake, and it's set up for our recent CMake and stuff. So anyway, so that's what I would recommend. And that's part of the reason we said, don't bother building the software on CentOS, because we're going to run it on Ubuntu. So here we go. Same kind of first step. Well, launch a new instance, select the F1 2 extra large, and everything else, select Ubuntu image, Amazon machine image, and or Debian, and away you go. SH the instance using that same key pair that you used before. Check out the software. It's a different machine, so a whole new experience. Now, instead of changing into the hardware directory, we'll just change into Sith AWS FPGA. Again, there's some dependencies, and so we'll run a script to install those. You can look at the script. It's pretty short. apt-get install several things. Some libraries, ELF library for the loader and CMake and stuff, and then run build. And this one, I just said build again to be consistent, but it's really make a build directory, change in the build directory, run CMake, run make, you're done, it's built. This is really fast. It's really nice. So then the next step is load the FPGA. And now we don't actually have the bitstream in our hands. We just have an identifier, which came out at the end of the build. It prints it and it writes it to a file, latest FPGA image, .json. And so we load the local image. This is a utility that comes out of that AWS FPGA repository. It's built when you set things up. Load it based on the global AGFI number. And then we install insmod the driver that's needed to connect the hardware and software pieces. And that will be built in that build.sh step in the previous step. All right. So then the next step is we just want to run something. So we have some host software that does several things. You tell it which devices you want to have. And so here we're going to say, I want a UART console as opposed to a no console or as opposed to Virtio console. I have a block device, which is backed up by a file named rootfs.ext2, which is, when I ran this test, it was a Debian RISC-V root image. And it gives you two ways to connect to the network, slurp and ton. The ton tap interface is more flexible, and so we end up using that. If you want to connect to the outside world, if you want to be able to enable outside users to SSH into this thing, you have to use the ton interface. So anyways, we do --ton tap 0. DMA enabled. What the device tree is, the device tree describes the hardware resources to the Linux kernel. And then the last thing is an executable to load, or actually a couple of executables. This one loads a kernel and security monitor in the testlinux.elf and Aws Key.elf, which is a key that's a per device key that gets loaded separately from the kernel. You don't have to have two elf files, but that's what we were using. That's what I was using in this test with the enclave, the Flute enclave test machine. So it kicks off, it identifies the elf file for you and starts loading it, loads it. And then here you see the kernel messages is starting to boot. It's looking at the flattened device tree, nice kernel version. And so after printing some more messages, Linux boots to the point where we can log in, we can run uname, we can see that it's a RISC-V 64 Linux system, run applications and so forth. And so the summary was, we designed processors in Bsv. When we put it on Amazon, we designed all the hardware in Bsv. Used Connectal to connect the hardware and software pieces pretty easily. And then used TinyMU so we could reuse device model implementations, reuse device drivers, and get the devices we needed attached to our SoC. So we could bring up Linux and test higher level functionality while running this thing on a FPGA. Running a simulation would be way too slow. Running at QEMU wouldn't test our hardware. So it seemed like a good solution. And it enabled the hardware side to be hardware designers to focus on the security enhancements, either development of those or formal verification with theorem proving and model checking, and enabled the Sanctum software developer to focus on his part. He developed and debugged in QEMU. We deployed on Amazon as a way of integrating them all together and making it available to the bunch of security researchers who are trying to exploit the system. So I would say it worked out pretty well overall, and I think there's some reusable lessons in this approach. And now I take questions, and we can questions now or discussions elsewhere online someplace. Thanks for your attention.